Welcome to another Draft Science presentation. So, a Ken Wheeler video, I guess. We'll try to stay on the subject, but I might drift off into other things. We'll see how the timing goes. So it's mostly magnets, but strangely, I think that is related to a couple of other subjects like gravity and, what's the other one? Drag. But anyway, drag in outer space kind of drag. What do you call it? Force drag? Ether drag? Anyway, so the V21, who I don't know if that's Ricky D or not, because I didn't block him for being just too rude. So he made this contention that Ken Wheeler has a video where he somehow proves that magnets fall at a different speed depending on how they're arranged with each other. And the other guy posted a 1/2 G times M12 or whatever kind of formula, like somehow it's half as falls half the rate of the other magnet or some kind of nonsense like that. And clearly, because I'm a rational person, I said, gee, that just sounds like complete and utter nonsense because there's no evidence of that. So anyway, this guy is now saying that this other Ken video that I did see and I didn't play because it's just so stupid. But now that you brought it up, I might as well show how Ken doesn't really know crap about magnets. Anyway, Gary, here's the video of Ken smashing together magnets. It would seem dangerous to try to replicate. Well, it's not as dangerous as you think, since the magnets seem very strong. So let's go to the silly video. I believe this is it. Yes. Alright, so Ken Wheeler magnets video. And it's not reloading very quickly. I can probably speed this up if it loads. Come on, YouTube. Speed it up a little, baby. Come on.
Well, here we go.
Yeah.
It's the most powerful one I've ever made. I scared the crap out of myself screwing this together. I gave myself a redundant bolt in case the threads strip. These are 2x2 by 1 inch neodymium.
So he had them before. He had a previous video to this. They had them smashed together with a coil of wire between them. So I guess that was going to prove something, but apparently that experiment wasn't very useful. So this is what they mean by smashing together. It's just pushing them together and using some mechanism like a vise or something. You crank them together and then you clamp them in that position. Even a bar clamp seems to me suffice for this purpose. As long as you're doing it on the floor or something. See, the key thing is you can't let the magnets turn or flip. That's the key thing. Because that's what they really want to do, and that's sort of an interesting concept, the flipping strength of magnets. I've never really seen that analyzed anywhere. I mean, it's sort of an obscure subject, so maybe somebody has studied it extensively, but I haven't fallen across it any when I just was thinking about it an hour ago. You never see any analysis, because it does seem that magnets, when you play with them, they have the flipping capacity is incredible. They flip so fast, much faster than they repel or attract. They seem to flip, inordinately quickly for any kind of Maxwellian force to explain. It seems a little outside of Maxwell's math to explain the flipping speed. Because I'm tending to think it's really another thing that just fits with my theory. It's because of the change in direction of the force. It's going perpendicular, and that's why it's creating so much flipping powers, because the gravity is completely reoriented around the magnet. It will balance when it gets to the new position, but as long as it's not in the right position, it's essentially a gravitational force that's flipping the magnets. I mean, I know that sounds... What? Well, I'll do some pictures later, as I'll try to explain.
And borons screwed together against their will, so to say. Right now, these either want to explode or actually break apart and fly together at about 600 miles per hour and destroy.
Yes, right. So, yes, but see, the key word he says, see, they break apart and explode. That probably can't happen because of what I just mentioned. Even if the magnet cracks, anything that gives it freedom, it's going to use that freedom to turn and attract. So explosion doesn't seem in the cards.
Anything that gets in their way. They have actually a unique, I'll show you later underneath the ferrocell, a unique field geometry outside, since everything operates off the right-hand rule.
Didn't do that yet, and obviously that wasn't so unique there. 2 lines of whatever he calls it, of go no further. Damn, YouTube's a little sloppy.
I like polarities. I don't want to get my fingers too close.
Don't want to get too close.
The interesting thing is we actually have a static force here.
Okay, so yeah, this part I also liked, was the static force part. Alright, so we'll get into that, but first I'll just point out an example that was kind of interesting of this effect. Was on 60 symbols. So they essentially did the kinetic ball thing, but just used a ramp. So it's like the swinging balls, except they have balls, and then they have one that comes in and crashes in, and then one flies off the other end on a ramp. And the interesting thing was, well, it's not, they didn't really do a whole oval, so it would have been more interesting if they actually did duplicate it, but anyway. So instead of one of the balls, they put a neodymium magnet. So they have a neodymium magnet at one end, and then 5 balls, and then another ball is going to come in and hit it. So the ball comes in really, really slow. To do the demonstration, they let it come in really slow, and the magnet speeds it up, and then it hits the magnet, and the ball at the end flies off. Incredibly exact. So the ball comes in really slow, the ball leaves incredibly fast. But see, the trick is, when this ball comes back down, this ball is going to be close to the magnet, right next to it, and it's just going to bounce off a little tiny distance and then smash right back into it again, and the ball will fly off the end again. So if they would have done it, it would have been interesting to see if it just keeps doing that for how long. I mean, there's more friction in a system like that, so it won't last as long. But it would have been nice if they actually did it the right way. But it just sort of points out the conservation. That say if you put the neodymium in the middle with 2 metal balls on either side, and then swing a ball through, you'll get the old effect, but it won't be any stronger or weaker. So it's still a conservative force, but it's really, magnets can really accelerate things. Strong magnets. Alright, so now we're on a static force. So by a static force, he kind of, I think, means a force not being created by any obvious motion, I guess. See, gravity would be a static force, right? I mean, you don't see anything creating the gravity. There's no mechanism. The Earth doesn't burn any fuel to make the moon stick to it. And if the moon was still, we'd obviously see it just fly right in. It'd be just like a magnet. It would look like a magnet. A magnet would look like the Earth and moon if you could put something at the right speed and create a bowl or something for it to spin around in a curved surface. The little thing will keep spinning for quite a while if you have the right polarities. But it's hard to make a magnetic monopole.
And of all the equations found within science and physics, they actually cannot explain a static force like this.
Right, so it's explained in all the equations. In Einstein's equation, the static force essentially is explained as bent spacetime. In Maxwell's equations, it doesn't have to explain it, but they call it a virtual force, a virtual photon, so to speak. So the force is accounted for in the mathematics. Now, Ken Wheeler doesn't explain it either, beyond saying something kind of magical like there's a constant flow of stuff around magnets. So they're constantly moving, flowing ether around them with a perpetual ether flowing mechanism. And everybody sort of has that perception. I mean, I guess I am in the tiny minority to point out there is no flowing force around magnets. They're not flowing anything. The current is not moving outside the magnets. There's no force cycling. It's not happening. There's a filtering of an external force, but there's no internal force inside the magnet.
And it is an enormous force. I actually had to use 2 pair of pliers as leverage, one clamping onto the other one, to screw these this close together.
Well, you should have probably used a bigger bolt, and but whatever. It would be nice if you screwed them all the way together and said, "Look, I accomplished it. Aren't I cool?"
They're insanely powerful. Well, the most amazing thing, which I should have mentioned.
There really are power. I mean, those are like the $35 magnets. I mean, they're expensive each. So yes, there are powerful magnets.
This a few seconds ago. Right now they're sticking to the table. Of course, you can't see it. You actually have to feel it. I don't like to get my fingers too close to the magnets.
Alright, so see how high you pull just to get that off of there. Alright, so he's doing his experiment right next to a refrigerator, probably a little freezer actually. He has extras of everything. He's doing his magnet experiment right next to a device that has a bunch of magnets stuck on the outside of it. It actually has refrigerator magnets stuck on it. Yeah. He's doing his scientific experiment next to the refrigerator with magnets stuck on it. Didn't occur to him that maybe he should walk away from the refrigerator to do experiments.
Is when you actually step back and actually drop it, not literally drop it, but pretend to drop it. You
pretend to drop it, which is move it down and then move it up, which is pretending to drop it, which isn't really free falling, Ken. But anyway, so this is the quality. This is the typical quality of a Ken Wheeler science experiment. Look, I feel it, don't you? He says he can taste the South and North Pole on a magnet. That's what he says. He's a professional magnet sensor. He can taste polarization. These are experiments, and again, he's got 291 thumbs up for this video and only 24 thumbs down. 10-to-1 ratio, better than 11-to-1 ratio. I mean, Barnum was right. You can fool all of the assholes all of the time. Yeah. Fuck. I know that's not what he said, but close enough.
You get a resistance like you're pressing against memory foam. It's actually very fascinating.
Yeah, it's very fascinating, real technical experiment. So apparently from this, the other guy extrapolated that they'll gravitationally move differently in space, but there must be some other video where he says something about that.
Or if you actually try to pull away, you get a feeling like you're pulling your finger out of honey if it were deeply seated in honey.
Yes, that's because the refrigerator with the magnets on it. See, there's a little magnet right below the logo there. The refrigerator, you're moving it next to a ferrous iron object.
I wish you could actually sense that in the video, which of course you can't.
Yes, that's right. I wish you did an experiment that actually had a real, some sort of real technical restraint to it, some sort of control. I wish they weren't all placebo, fakey, voodoo, psychic surgery experiments.
Be careful, because these magnets are actually made out of ceramic. I mean, they do break. I mean, they're ceramic. It's no different than a piece of, like, Corningware.
It's a lot different, actually. The ceramic's a little bit more, it has a little more rigidity than that. Likely because of the neodymium. But anyway, but yes, they're hard, but they crack easy. So I've had them where the two magnets, especially the little tiny strong neodymiums, the wafer type, where if you let them crash into each other, they'll just shatter, but they don't fly apart. The little pieces obviously stick right to each other. And in the case of this, because they're turned repulsively, like I said, what will happen as soon as something cracks and has some liberty to move, the first move it's going to make is turning, and then so it's not going to shoot out. It's going to turn and go in.
And that,
I mean, you could whack that thing with a hammer and pieces won't fly off. They'll just break off and crash into each other.
is the reason why I have a huge washer, a smaller washer, then a small washer, because if I actually just use the small washer on either side, then it would be unsupported.
Well, the reason why he's really doing it is because this giant hole, the hole is much larger in the magnet than the size of the thing you put through it, or else it's bored with it has a countersink on it. Maybe it's just a countersink. But yes, the washer idea is not a bad idea, quite obviously, but I don't think if he did the experiment the right way, can't be sure he's going to crack the magnets.
Mostly on one side, and it would actually explode. There's no.
So explode is something usually goes. You should say implode because it really won't explode. The magnet will crack. As soon as it cracks, the piece will turn and stick.
Way I could have gotten these that close together without the huge washer and the intermediate washer on either side, because they do want to go off like a gun. And the reason why I have a second wing nut here is that this one could easily strip, and then this magnet would actually go shooting off the rod. Like
yeah, I don't know if there's any evidence that it could easily strip, but that the magnets are that powerful. So that's just sort of talk. I mean, just sort of talk. I mean, you know, stripping a galvanized, looks like galvanized, you know, bolt would take a substantial amount of torque.
a gun. It wouldn't be pretty. Actually, as soon as it shot off like a gun, it would probably go far enough. It might actually circumambulate back to the other side.
Circumambulate. So I thank you for that. Circumambulate. Circumambulate. Never heard that two terms put together before, right? It might circumambulate. So it's you know, got a little scooter, and you know, it gets on its little rascal and it ambulates, you know, in a circular manner. I mean, just what the hell is that? Circumambulate. Who on earth is? I mean, type it into Google. Has anyone ever said circumambulate? No one's ever said that.
Destroy whatever got in its way. So the view from this underneath the ferrocell, I don't like touching it. Don't touch the magnets that want to explode. The view from underneath the ferrocell is
implode, but whatever.
Quite amazing. I wish you could feel it.
Oh, I wish I could feel the ferrocell. So just switching subjects. I wish I could feel the ferrocell.
Anyway, I wanted to make a large one of these, and this is as large as it gets without being really, really, really dangerous. Thank you so much for watching.
It says him again. Like I said, you could make a better tool for smashing them together, and then there won't be any danger at all. But it seems to me that I think the truth is, unless you whack it and put some extra force in to get the pieces flying in the right direction, you won't be able to make it explode. Alright, unless you can force the magnet not to turn, which you have to have a rail system or a tube. You have to have something that doesn't allow the magnets to turn to be able to shoot the magnet. Just like the kinetic ball can only go in one direction, and as soon as it tries to go in the other direction, it doesn't go anywhere. So it's a conservative force.
Here you are looking at static force, something no branch of science has ever...
Alright, so no branch of science has ever... Yes, I'll concede that all the things that do have the idea, that represent the push and pull in force form, that conventional science has a silly explanation. It's either bent space or some sort of virtual energy ton. Now, those are not good explanations. They're not physics. But your ether theory is likewise not physics, and it has absolutely no explanation for perpetually spinning vortexes. So you're in the same boat in terms of your explanation is unsatisfactory. I'll point out that mine works perfectly. Yeah.
Explained. Not static potential, not static energy, but static force. Something that no branch of science, go look it up if you don't believe me, no branch of...
Yes, well, again, they do account for it. They just don't, like you, they don't account for the origin of the energy, just like you don't can. You just say nature's a crack whore, or nature's not a crack whore, and therefore she has perpetual motion. Because you don't explain where the motion comes from, where the energy comes from, at all. So, I will move on to the drawing board and try to illustrate a couple of little
Science has ever explained a static
simple
force?
points.
Absolutely not. Repeat after me. Static force.
Yes.
Science has never explained it. Yeah.
Right. I have. Yes. So you're not paying attention. I have. I've explained it. Well, I mean, I've explained it in the sense that I've said you have to accept a universe that has force in it. You know, the photons exist, and they always existed, and you have to get to that point where you accept that whatever they always are that. That little bit's moving the speed of light.
Atomistic nonsense. Thank you for watching.
That's right. In conventional physics. So he thinks that bent space is atomistic. Bent space-time is an atomistic theory, when it completely has nothing to do with anything particle-like. But that's just part of his lie game. You know, he can't say anything. He doesn't accept counter-arguments.
Goodbye. If
Yes.
you like these videos, you can always drop a small donation in the link below.
Right, so I can buy more millions and millions of dollars worth of camera equipment. You know, it really is a Social Security policy. He's got a huge pension, gigantic pension. People eat that crap up for some reason, like Reverend Ike or something. They just fall for it. Some guy with diamond and gold rings and stuff, and they'll put money in his frickin' dish. It's just amazing how stupid people are. Fuck. Anyway, okay, so we'll move this down, I suppose, and that should move this up. That seemed to have worked adequately. Alright, so magnet. We'll draw one, probably. And so we'll just do the basic. I'll try to keep it simple, stupid. So there's force on the outside mixed, coming in all directions. And what's going to happen inside the magnet is, the black force will come out this side and this side, and the red force will come out here and here. And that is what makes magnetism. So mixed comes in, segregated comes out. And how it's getting segregated, I think, is why it turns so quickly. So gravitationally, this becomes neutral. So this is essentially gravity. Okay, this is gravity, mixed force. And this is essentially filtering gravity. Okay, but because it filters it evenly, I mean, it doesn't make any new little bits. It's gravitationally neutral. So it doesn't affect the gravitational effect. It's just segregating the elements in the gravity. But it's not really affecting the thing gravitationally. But the interesting effect is, so let's say a red thing is coming in. And I guess we'll use dotted lines to help. Now you can look at it two ways. The little red thing goes right through the black stuff and just comes out the red end. Let's say it comes in this way. Okay, so red comes in this way. Somehow it has to come out this way. So there's two ways to think of that. That it sort of has to, I mean, theoretically, to make any sense, it kind of has to do some sort of angular thing. Where it comes out this way. Or it has to do some sort of right turn thing, and then it comes out this way. And I'm big on this right turn thing. So I'm thinking that all of this ends up being right turns. So force that comes in this way, the black can't come in, it reflects. So it has to be red, the opposite force. And when it comes in the black, see, it can't just, if it comes in and turns right here, that's not going to work. Well, it might. Because obviously the sides of the magnet aren't quite as strong as the top and the bottom. I'd say I'm just getting to the point that the magnet actually does turn. So it's the one that comes in, say, at an angle this way, and then it comes out this way. That'll still work. So yeah, there could be some leakage going out the sides that's still red, and that accounts for the fact that these lines here, the compass needle stays pretty flat because there's a balance of force, and it's only at the ends where it really starts to dramatically turn. So anyway, so that's the part we're really talking about, is the fact that there's this tendency, if I put another strong magnet and I put it facing this magnet going the same way, that the repulsion, and this is going to be repulsive, but somehow instead of just flying away, what's going to happen is the magnet's going to flip and then stick. So there's a pretty strong tendency to turn. Now you could say it's only because by randomness you never get it perfectly perpendicular, and so it always starts a little bit off, and that little bit that's off makes it turn even more. But I don't think that's a very good argument. So I think it's this effect, is that because the forces are coming in, the amount of force coming in this side ends up coming out of here, and the amount of force coming in here ends up coming out of here. So there's a slight change in the sense that it's not only just filtering the force, it's filtering the strength of the force. So it's making the force stronger here and weaker here. And that's why now gravity is going to affect it different, because of how the forces are different. So something like that. So it's just an indication of an effect. Now the part that relates to drag, I was just thinking about attraction, and the fact that when a magnet's attracting, it means there's less force between the two. So put it this way. So it just means that because all the red force leaves the black and all the black force leaves the red, that there's no reflections in here going back and forth, and so that's why the magnets attract. So the same kind of argument could be used for velocity, in the sense if you thought of velocity as a magnet that has been like barred, then you could sort of understand that there's fewer reflections because of, the black stuff is going through these black areas and the red stuff is going through the red areas. Did I say that right? Yeah, there's no reflections in those halves. And so thereby reducing the overall pressure, because all red force that hits black force goes through. None of it ends up hitting anything red, because there's anything red, yeah, so there's absolutely no reds here. So all of these reds get through, where technically a red here, if it was mixed, would not be able to get through. It would hit a red somewhere in the substance, so somewhere in the path. So if I just spread out the reds, you can sort of understand that if a red's going through this obstacle course, it's inevitable. It might hit one here, it might hit one here, it might hit one here, but it's going to hit a red. But if there's no reds, and it's just all blacks, and it goes right through the blacks, or, well, it goes perpendicularly out, but doesn't mean anything. The perpendicular doesn't use any force. That's sort of what the magnets are demonstrating, that moving this red force and having it go out this way doesn't create any forward momentum. So the turn is for free. It's a non-momentum event, where the reflection is a momentum event. You know, the thing hits, a piece goes this way, this thing has to go this way. The turn is for free. All right. So you can sort of understand, though, that if you just think of it as a probability equation, all the blacks, if this thing was mixed, all the blacks would hit a black somewhere, and all the reds would hit a red somewhere if it's mixed. But if I segregate it, half the blacks and half the reds hit nothing. And that would be an incredible ease to passage. So I think that might be related to the ether drag problem, the idea that a particle theory creates drag when something moves. When something has velocity, it will be moving against the static force, as Ken Wheeler puts it, gravity. And moving against that static force would create more force in front of you than behind you. But if you're dissipating more force, becoming more transparent as you're moving into the force, by allowing force to go right through you, then the drag would be mitigated. The catch would be is that nothing material could probably travel more than half the speed of light. So at more than half the speed of light, this might not work. So, but all this stuff that goes, the material stuff that goes very fast, frankly, our measurements of those speeds are not very exact. Not confirmed by substantial evidence. Clearly observed evidence. Alright, so I think that's I think I'll leave it a Ken Wheeler style video and not go into the other lensing subject. I'll save that for another time. So is there anything else on Ken Wheeler thing? So yeah, so magnets will break, but they'll flip, and like I said, I don't know if anybody has any knowledge of any kind of, whether they've done any real analysis of the strength of that flip, but it's substantially strong, and I don't think Maxwell's equations really do account for it. Yeah, but I think it has to do with the fact that the flip is being instigated partially by the fact that for gravity work, there has to be another object within your realm. So it's ironically both gravity and magnetism that is in relationship between the two magnets. And the gravity effect is being magnified. So there's not only just the magnetic effect of the polarization, there's a true gravitational change because your gravity is leaving perpendicular instead of going straight. Yeah. I mean, it's a little complicated to explain, but the flip is actually a reaction to the distortion in the gravitational field by filtering the magnetism, where the attraction and repulsion is the magnetic effect, but the flipping is a gravitational effect. It's a pretty subtle thing, and I've only been thinking about it for 2 hours, but I think I think there might be something there. But again, it takes a bit of research to see if there's something is there, because I don't know if too many people have actually analyzed the flipping strength of magnets. So anyway, till the next time.